If we want to find the distance that an object travels when thrown as a projectile at a diagonal angle, the idea here is we have to take the diagonal initial velocity and separate it into x and y components, and then solve in the x and y component problems separately in order to get a final answer. Now, let's say we are focusing on finding the horizontal displacement of such a parabolic projectile path, right? So first things first, right? We got to separate v into its components. The opposite of theta component of this velocity of the little triangle is going to be related to sine of theta because of the SOHCAHTOA relationship. So sine of theta will equal this, this y variable divided by the hypotenuse, which is v. So the y coordinate of the velocity will be equal to v times sine theta. So I'm just going to write that there. So this component is v sine theta. Similar argument for the adjacent side down here. It'll have a magnitude of v cosine theta. Now, if we're writing the kinematic equations for the x-coordinate system, what we're looking at is the x-coordinate is going to have no horizontal acceleration. So in the displacement equation, the a term is going to go to 0, and we only have to worry about the initial velocity multiplied by the time. So the displacement in the x direction for a projectile like this is going to equal the initial x velocity, which was v cosine theta, multiplied by the time that it takes for this thing to fly through the air and hit the ground. Now, of course, the problem is we don't know what the time it takes is. It's not given in the problem, right? It's left unstated. The only things we have here are v, and we're supposed to solve for d. We have v and theta, and we're solving for d. So we have to eliminate t somehow. The goal is to eliminate t, and the other tool that we have to accomplish this is going to be the entire other dimension of the problem that we've ignored up to now, right, which is the y dimension. So for the y-coordinate system, the vertical direction of this problem, the displacement over the course of the same flight path, right, is technically 0 because it begins the problem at a height of 0, and it ends the problem at a height of 0. So the change from 0 to 0 is a grand total of nothing. So when we're filling out displacement equals 1/2 at squared plus v0t, the displacement is now 0 for y. The acceleration in the y direction is negative g because gravity is pulling it down. T squared plus the initial y velocity is v sine theta, so that goes there, times t. Now, our goal was to solve for t in the y equation so we can plug it back into the x equation to solve for the distance. So this is a quadratic equation in terms of t. So to solve quadratics, we need to factor. We're going to factor t out. That leaves us with negative g over 2 times t inside plus v sine theta equals 0. And solving for t involves setting the factors equal to 0. So we get one solution at t equals 0, and we get a second solution when the second factor equals 0. And if you solve for t here, let me just write it out. Negative g over 2 t plus v sine theta equals 0. You would subtract this to the other side, and then multiply by 2 and divide by negative g. So the negatives would cancel, and the time in the air is 2v sine theta over g. What we can do here is we can plug this back into distance, right, for the x equation. So if we plug into here, from here, right, distance is equal to, we're going to get v cosine theta times t, which is 2v sine theta over g. So altogether, the distance, the horizontal distance that a projectile will fly if you launch it at an angle of theta at a velocity of v is 2v squared sine theta cosine theta over g. Now, that's a super useful result.